classes? Sorry, I don't know that. Oh, okay.
I only have 15 allowed slides.
Oh, okay.
So I have to make all 3 classes work on 15 allowed slides.
Okay.
So no, pre-cal shares, Algebra 2 share, calculus gets its own, but.
They're special.
Okay, guys, yesterday we started talking about continuity, and we started talking about holes and asymptotes. And basically all we talked about was a little bit about holes, right? Okay, so the idea, holes or asymptotes, in general, are going to be whenever your denominator equals 0. If there's a spot that your denominator equals 0, that's either going to be a hole or an asymptote. Now, in this case, our denominator equals 0 at x plus 2, right? And so we're going to find that something is going on at x equals negative 2. Because the top factored, right? The top factored into x plus 2, x minus 2, and because this factor cancels, that tells me it's a hole. And I think I suggested to some of you graph this. And if you graph it, it's a line. And technically, there's a hole at x equals negative 2. Not that you can really see it. If you trace it, you might be able to catch it. If you zoom in enough, you might be able to catch it. But it's not really visible. But we know there's a hole there. That value does not exist. It is called a removable discontinuity. Okay? Holes are called removable discontinuities. As opposed to asymptotes. And specifically, we're talking about vertical asymptotes here. So I feel like I should kind of mention that. This is a vertical asymptote we're talking about. And the difference with a vertical asymptote, okay, well, if I set this denominator equal to 0, x minus 3 equals 0, we solve that, there's going to be something happening at x equals 3. Which this is going to say x cannot equal 3. Now, does that x minus 3 factor cancel with what's on top? No, there'd have to be another x minus 3 factor on top to cancel, and there's not. So because x minus 3 does not have a matching factor on top, and it does not cancel, this is an asymptote. Okay, so for that reason, because nothing canceled, we know it's an asymptote, and I don't know why I need to be specific. It is a vertical asymptote. This is our way to find vertical asymptotes. And vertical asymptotes are non-removable discontinuities. Okay, non-removable discontinuities are what vertical asymptotes are. Okay, know the difference here. Know the difference. Okay, let's look at 2 quick examples. Determine whether the function has a discontinuity. So if it has a discontinuity, does it have a hole or vertical asymptote? In other words, is there some place the denominator would equal 0? Because that's going to create a discontinuity. And then state whether it's removable or non-removable. So, on A, is there going to be a discontinuity of some sort? Yes, where at? At negative 3, because you need to take the denominator, x plus 3, set it equal to 0, and when you do that, we're going to get x equals negative 3, which means x cannot equal negative 3, right? Okay, so now the key is it a hole, because there's a factor of x plus 3 on top that can cancel, or is it a vertical asymptote, because there's no factor of x plus 3 on top that can cancel? And here's the key.
That factor.
Does it factor? I don't know if you guys know how to factor. I'm trying to remember, did we factor these in Algebra 2 or not? I don't remember. Did we factor sum of cubes?
I feel like I did, but I don't really remember.
See, but that doesn't mean I taught it, like,
I don't remember. So.
I feel like I might have done it in Algebra 2, we just might not have spent a whole lot of time on it.
If we did, I feel like it might have been like one or two.
So, okay, this is of the form, and I'm not going to spend a bunch of time on this, okay? It's not a huge issue that we're going to spend a lot of time on right now. But to give you the form, I'm going to put mine over here. This is of the form a cubed plus b cubed. And a cubed plus b cubed factors into one factor that is the cube roots, a plus b, and the other factor that is the first cube root squared, so a squared, opposite sign now, minus ab, and plus b squared. Okay, so I taught it in Algebra 2,
Yeah.
because there's some,
Shoot, yeah, I remember that. That's
okay, there's a little bit of familiarity. I'm not saying you remember. Okay, I'm not holding you responsible for it right now.
I definitely
Now.
do this.
You did or did not?
Did not.
Okay. And see, that's the thing. I can't vouch for what you did. I can't vouch for what Connor did. I can't vouch for Donna and Emma. Kylie, it would have been 2 years ago. I mean, I can vouch for it, but it would have been 2 years ago, So, Hannah, I don't know when you left. Like, I can't vouch for exactly where everybody's at, but I can say what I did or didn't do last year. So, okay, here's the deal. So this is of that form. And so it does factor. And what we're going to factor, I'm just going to put it up top here. The first is a binomial. What is the cube root of x cubed? X. My sign right now stays the same, so it's going to stay plus. What is the cube root of 27?
3.
3, because 3 times 3 is 9, times 3 is 27, yes? So my first factor is x plus 3. Right there, we have something that cancels, right? Now, the trinomial. The first piece in the trinomial is the first cube root squared. So if we take x and square, we're going to get x squared. The next piece, we always change the sign. So since my original problem in first parentheses was plus, this is a minus. And then I always say it's my two pieces from the first parenthesis multiplied together. So it's the two cube roots, which were x and 3, multiplied together. X times 3 is 3x. The last term is always a plus, and it's the second cube root squared. So 3 squared is 9. So, does a factor cancel? Yeah. X plus 3 cancels with x plus 3. So, because the x plus 3's cancel, that tells me that at x equals -3, there is a what? A hole. Okay? And is that removable or non-removable? It's what? It is removable. So we have a removable discontinuity at x equals -3. What did you ask?
What does it mean when it's removable and non-removable?
So removable and non-removable are just two names to classify. I think of, when I think removable, I mean, it's a hole, obviously. And so I think, like, I could remove a hole, I could plug a hole. Like, I don't know, it's kind of my weird way of, thinking about. Non-removable is an asymptote, right? I can't just, removing an asymptote doesn't fix the graph, so to speak, because the graph is still split and going weird, different directions. So it's a name to describe that type of discontinuity. Okay? Questions on that one? Other than the factory might have been a little different. Okay. And realize there's also, with a cubed minus b cubed, there's a slightly different setup, right? And it would just change. Let's see, do I dare try? If it had been a cubed minus b cubed, this would be a minus b, and this would be plus ab there. Those are the signs that change. This guy still says plus. Everybody else is the same. Okay, in case you're curious. Okay, B. Thoughts on B? Is there a discontinuity? Yes, because is there a place my denominator will equal 0? Yes. Where will my denominator equal 0? You set x minus 2 equal to 0. At x equals 2, we have an issue. Okay? Now, the key is, and I'd like you to be able to do this without graphing, is it a whole or it is a vertical asymptote? So what we need to investigate is the numerator. Does my numerator factor? It does. Product and sum. X squared breaks into x and x. What multiplies to be 2 and adds to be 3.
2.
And they are both positives. What factor cancels? Okay, we factored it, but nothing still cancels. So what does that mean about this discontinuity? Okay, it's a vertical asymptote, which means it is a non-removable discontinuity. Okay. So vertical asymptote. Specific name is non-removable discontinuity. And that non-removable discontinuity is at x equals 2. You know, Noah's complaining it's a lot of writing, and I'm sitting up here in my head, discontinuity. Like, that's a word I struggle with spelling. And so, yes.
There's like a big cricket thing on the floor right there. It's just crawling towards your desk.
Towards my desk.
Yeah, it
Is
was
it okay? Now you
under
gotta
the
talk
chair. It's like, I think it's a cricket.
Is that what the discussion was behind me?
Yeah.
I heard like whispering
Well,
over
it
here, and I'm
started
like,
moving towards me.
I went
So
under
I
the
can't
now
see
it
it.
disappeared. It must really be under my
Oh,
desk.
it's like behind the
I see
chair.
it. There it is.
Oh, yeah, there it is.
Oh,
That's just
yeah, it's a cricket. Stay quiet, buddy.
it's a pretty move.
It's 90. Oh, I see.
Yeah.
Wait till you hear it say
That's Jamal now.
Stay up here. Leave everybody alone out there.
Jamal.
I'll deal with you later.
If it comes over here, I'm telling it.
Like I say, it will.
Not bad.
Okay. Got an idea of removable versus non-removable, yes?
He's a
Now, we didn't do it, and I'm not going to take the time to. This one we just did. Could you graph it on your calculator?
Yeah.
Would you see, well, you wouldn't physically see the asymptote, but would you see the graph representing an asymptote?
Yeah.
Yeah, because your graph is going to go, you've got one piece going up, one piece going down, which indicates that there is an asymptote. On this graph, it's going to look like a regular graph. You're not going to see an asymptote. You might be able to find a hole if you zoom in close enough. Okay? Okay, so graphing is kind of a backup plan or a check yourself plan. I want you to be able to do this algebraically. Okay? What's wrong?
It looks really weird. I don't see it.
There is an asymptote because, so let me do a zoom fit.
Whatever feels right.
Zoom fit shows you there's a piece you couldn't see because it was so far up. Now do you see a vertical asymptote?
And you can see how it's at 2.
Okay.
Wow.
Okay, guys.
No.
Increasing and decreasing functions. Okay, in a way, pre-calc is behind this year. I already taught increasing and decreasing functions to Algebra 2. To this year's Algebra 2 students. I didn't teach it to you guys last year. It wasn't in my curriculum, and I don't know if it's explicitly in the standards, but okay. So, if a function is considered increasing, then as the x value increases, so as the x value increases, we're moving to the right, yes? As the x value increases, so does the y value. So that's saying as you move across the graph to the right, your graph is going up. Thus, here is your increasing idea. Basically, when we talk increasing, the graph is going up. And it's as the x value increases, so does the y value. So x goes up and y goes up. The opposite of increasing is to decrease. Now, notice here, it says as the x value increases. And what that's saying is as you read across the graph to the right. That's what that is indicating. So as my x value decreases, what does the y value do? Excuse me. As the x value increases, what does the y value do? Decreases. And so that's saying as x increases, so as I move across my graph to the right, my y value is going to be going down. It's going to be getting smaller, and thus we end up decreasing. Now, most graphs are either increasing or decreasing. Occasionally we get a third option, which is constant. As an x value increases, so again, as x value increases means as we move across the graph to the right, the y value does what?
Stays constant.
It stays constant. I don't even know how to draw an arrow for that one. It just, so basically, what's a constant graph?
Straight.
It's a horizontal line. Okay, a constant graph is a horizontal line. Okay, so increasing, decreasing, or constant are my options. Okay, for each function, tell the intervals on which it is increasing or decreasing. Now, when we tell the intervals on which it is increasing or decreasing, realize we're going to use x values to do this. It's probably the hardest part, is just realizing we're using x values to do this. So, what do we need to do here? We need to graph this. As you graph this, actually, you know what this is. I mean, yes, still graph it, that's fine. I'm not going to graph this one on the screen, but what is x plus 2 squared? It's a parabola. Officially, it's going to be a parabola moved to the left, correct? Okay, so I'm not putting it on, the key point we're going to need is where is this minimum value at, and it's at -2, 0, correct? So you got a parabola, it's at -2, 0. That's all the information I need, honestly, to do this problem. Now, I always start on the left-hand side of my graphs. As I start tracing my graph, as I start tracing that parabola on the left side, what's the first thing I'm going to do? Am I increasing, decreasing, or constant? What am I doing here as I start tracing this? I'm decreasing, yes? My graph is moving down. How far do I decrease? When am I going to stop decreasing?
When you start increasing.
So when am I going to start increasing?
To 0.
Okay, at that minimum, yes? So I am decreasing. Okay, the first thing I'm going to do is I am decreasing. Because as I move towards the right on my graph, I'm going down. Now, the interval here. We're going to use interval notation. When did I start decreasing? Yeah, when did my graph start? My graph starts way out there. Okay, so we start decreasing at -infinity, which always uses parenthesis. When am I stopping decreasing? At this point, -2, 0, the value I need here is -2, because that is my x value. Now, parenthesis or bracket. And the question is, does my graph, well...
Technically, directly on -2, 0, wouldn't it be a constant? Whatever, so wouldn't it be parentheses? Because at that point,
I think you could argue both ways on this, honestly. I look at it as the fact, does my graph, do I touch -2? And does my graph touch the value -2?
Yeah.
It does. So I use brackets. However, because that -2 is that break point, I could see you argue both ways. Does that make sense? Okay. So now, after we pass through -2, 0, what do? Now, as we continue to move right, we are moving up. As we move up, that is increasing. When did I start increasing?
-2.
Okay. When we stopped decreasing, right? So -2, parenthesis or bracket.
Bracket.
I would say bracket, again, I could understand if you want to argue parentheses there. I've seen it done both ways, I guess. Increasing, increasing, increasing. When do I stop increasing? Infinity. Positive infinity. Okay.
Really good at writing infinity signs.
We've done a lot of infinity signs lately, haven't we?
I feel like that might have done it. Oh my god.
I had to look because I meme I put up almost involved an infinity sign, but then I changed my mind at the last minute and I put up that one instead. So, okay. Let's look at B. G of x is x squared over x squared minus 1. Well, what should you be doing right now? You should graph that. I'll be honest, I don't know what that graph looks like off the top of my head.
It's kind of funky.
It is kind of funky. I mean, I have it here in my graph. So get it graphed because you're going to need to be able to look at some things and examine some things.
My graph doesn't
I feel like
graph.
it must be a person.
Actually, I think I'm going to graph this one on the screen.
No, look, like there's 2 eyes and there's a tail.
That's not nice.
Making her graph a person.
No, but like, remember on Minecraft they had like those little block people?
What? So I have a question. Do you think the infinity sign kind of looks like a pring?
Like a what?
A pring ring, like the chin? Because like when you draw it, you kind of.
Oh my gosh!
Obviously, Sophie does.
You can't tell me that.
I mean, the way you made it.
Okay, that one. Not that one. But that one looks like a Pringle.
What?
Okay.
No,
Not
the
the
way
way
you
everybody
made it,
else
it looks like.
Infinity signs look like Pringles, according to second hour pre-calc.
They do, but that's not how I make mine.
Okay.
I don't do the two lines.
Okay. B.
It's sweet.
Did you look at your graph?
That's a pring.
Yes.
So this graph is broken up into 3 parts, correct?
I don't know the other.
Math. No more Pringles. Math.
You can do math and Pringles.
Yeah. You can count Pringles.
So as you can see, this graph goes all the way up to Pringle.
Okay, now, there's some important information we need to know before we start talking about increasing, decreasing. The last problem, we had to know the minimum of that parabola. Okay, because that was a breakpoint. Here, we're going to have to know some other information. So, can you figure out, you obviously see 2 asymptotes happening, yes? How can you tell me where the asymptotes are? And I'm not necessarily saying based on the graph.
Algebraic.
Algebraically.
Really, really skinny.
I mean, that would be kind of.
But algebraically, I want to know what numbers these asymptotes are at, what x values. How can I tell algebraically?
Can you trace it? Well, I guess not.
No, that's graphically. Algebraically. It doesn't cancel, but how can you find the values? You're overlooking it.
Oh, it's -1.
Set the denominator equal to 0. Okay, now, either set the denominator equal to 0 as is, or could you look at this as factors? X squared minus 1 factors into x plus 1 and x minus 1, doesn't it? So where are these vertical asymptotes going to be at? One's going to be at -1, the other's going to be at +1, yes? Okay, those are numbers we're going to need to know. And being able to look at this and say, oh, okay, this denominator tells me that information. Okay. As I start the left side, what's the first thing my graph is doing?
I'd say that's increasing. Yeah. First.
As I start the very left-hand side, my graph is increasing, correct?
It's pretty steady increase.
So my first interval I'm going to talk about is going to be an increasing interval. Now, I have to just stop right here at this asymptote and not, I can't connect. We have to just worry about that. So when does my graph start increasing?
Rainbow.
Negative infinity. And when do we stop increasing?
Positive infinity.
What x value do we stop increasing at? The y value is going up to positive infinity. But what x value is this represented as? Negative 1. So our first increasing interval is negative infinity to negative 1. Because we started over at the left, and we're going up, we're going up, we're going up, and then my increasing is going up to positive infinity. But the x value that's going to prevent me from going any farther is negative 1. That negative 1 is an asymptote. So am I going to use a parenthesis or a bracket? I'm going to use a parenthesis because we're not ever going to touch negative 1.
I wrote a
Okay,
but I said.
so now we're going to skip over the asymptote, and now we're going to go, as we continue left, we're going to go across the next part. So the next piece I'm going to do is I'm going to go straight down here to the bottom. What am I doing here on the left side of this parabola?
I'd say you're increasing.
Are we moving up again?
Yes.
Yeah, we're increasing. When do I stop increasing?
0, 0.
Tip.
Okay. Whatever that vertex is. What is the vertex of that parabola?
0, 0.
Is it 0, 0? My graph turned off.
I did the little trace, but
Okay. So, we need to know that, right? So now, okay, work with me. We have another increasing interval. When did this piece of the graph start increasing? No. What x value? It's coming from the y value, negative infinity, but at what x value?
negative
1.
Negative 1. Negative 1 with a
parentheses.
parenthesis because negative 1 is the asymptote. And we're increasing, 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 increasing. When do I stop increasing?
0.
0.
This vertex of 0, 0, and the x value is 0. 0 with a parenthesis or bracket.
Right. This would be a bracket.
This would be a bracket because we touched the point. It is a point. It's not an asymptote. Okay. What happens after we go through the top of the vertex?
It starts to get better.
We start decreasing. As we continue right across the graph, we are decreasing. When do we start decreasing? At 0 with a bracket. When do we stop decreasing?
1.
It goes to negative infinity, but the x value
Just 1.
is 1 with a parenthesis. It's an asymptote, so I use parenthesis
Why is there a comma?
because it's interval notation.
It's gonna be
Are you talking about this comma?
No.
This comma,
Yes.
as opposed to a union?
Yeah.
You could go either way. We're really just listing individual intervals, though, so you can go either way. Okay, so now I pick up. Now we're going to continue to move right a little bit. So my graph is here. What is my graph doing here on the right side of the asymptote? It's decreasing. Okay. When does it start decreasing? At what x value? At 1. It's coming from a y value of positive infinity, but it starts decreasing at 1. I wrote it without asking. 1 with a parenthesis. When do we stop decreasing? That is the x value positive infinity because it goes off forever.
So,
Good team.
It's a parenthesis.
Okay,
I
Now.
wrote down parentheses.
I'm running out of time. So, focus.
Okay.
Boundedness. Okay,
I like that word.
boundedness. In my brain, it's very obvious, but I struggle to figure out how the best way to explain this. I don't know. It's one thing I struggle to, find a good way to explain. But okay, so the following examples are how graphs are bounded. So a graph can be bounded above, which if it's bounded above, there's a top boundary that it does not go above. Okay? If it's bounded below, there's a bottom boundary. It doesn't go below. And I'm not saying it's a physical boundary. There's just a spot it doesn't go below. If it's bounded, that means there's an above boundary and a below boundary, and it stays between those two. And then if it's not bounded, it goes infinitely up, infinitely down.
Unbounded.
Okay, so, for example, this one is not bounded above because it's going up, right? It's going up to infinity. There's no stopping it. It's not bounded below because it's going infinitely down, right? I can't contain this graph. So this one is what we would just call not bounded. Now, this next example, it's not bounded above because what's going on? It's going up, so that's why it's not bounded above. It's bounded below.
It doesn't.
Is there a spot it never goes below?
Yes.
Yeah, it's never going to go below right there, right? That's a boundary I just drew in, but that's our boundary. So this is an example of a graph that is bounded below. It does not cross that invisible line right there. So you're not going to see a physical boundary. It's just a spot it does not cross. The next one, is it bounded above?
Yes.
Yeah, there is a boundary above, and not a physical boundary, but there's a spot above that we never cross. What about below? No, it's going to keep going infinitely down. So this is an example of a graph that is bounded above. And then my last graph is an example that is bounded. And when you use the words bound, when you just say bounded, that means it's bounded both above and below. Now, for this to really work, it's not a great graph. Think of these endpoints as, it's not drawn great, it's kind of blurry. Think of them more as dots. I think is the easiest way to think about this. And if we think of them as dots, you see a spot it doesn't go below, and you see a spot it doesn't go above. Okay, you guys aren't familiar with sine and cosine curves, but they are excellent examples of bounded. Okay, so how do you do A and B?
Graph.
You graph them. Now, what is 3x squared minus 4?
Parabola.
Parabola that opens up how?
Upwards.
Okay. I had to process upside down rainbow. Okay, I'll agree.
Did you just say upside down?
Yeah.
Okay. Okay, so it's a U shape. It's a right side of U is what I say it. Now, with that in mind, is this bounded at all?
Yeah, and the below.
Where is it bounded?
Drop below.
Okay, focus please. This is an example that is bounded below. Is it bounded above? No, it's a parabola. It is going up infinitely. Now, not that you have to know this, and I don't know if you have to state it, but where is it bounded below?
-4.
At y equals -4. As I said, my focus is just, can you identify how it's bounded? Above, below, not bounded, bounded. And I think the book might say bounded on all domain, or it gives some, I can't remember, I'll have to look and see. Okay. B, have you graphed B?
Yeah.
It looks something like this. X over 1 plus x squared.
Whoa. I did too. That was fun. Made it look crazy.
Oh, there's a, okay, I couldn't see that spot in the next. Yeah, see, I don't like to fit on this one because you need the bigger
Yeah,
picture.
no, that is kind of weird.
Okay, so the graph looks something like this. What are your thoughts?
I say
Bounded.
Is there a spot on the bottom it never goes below? Yeah. Is there a spot above it never goes above?
Yep.
Yes. And so what is that then?
Bounded.
That is bounded.
This is definitely one of your favorite words.
Okay. Bounded, and as I said, when I say bounded, I mean above and below. Okay, real quick. I don't know if I have time to really teach something new on the calculator, but I'll have to clean it up tomorrow.
3 minutes.
Okay, extrema. You're probably not familiar with the word extrema. Extrema are the hills and the valleys of our graphs. Extrema, here's what you need to know. They are maximums or minimums. You know what a maximum or a minimum is, right?
Yes.
Maximum is the highest a graph ever goes. Minimum is the lowest a graph ever goes. So, an absolute, for instance, absolute is the highest or lowest point the graph ever goes. A local max and min, okay, so local max, that's a local max because is it the highest the graph ever goes? No, because it extends up here, but it's a high point. Local min, it's not the lowest it ever goes, but it's a low point on that piece of the graph. Okay? Here's an absolute min. Why is it absolute? My graph will never go any lower than that. Here's an absolute max. And this is supposed to be going over here, so what it's supposed to be doing. Because my graph will never go any higher. We're going to be graphing these. And in your calculator, there's second 0. You can do a 0. There's also max min on that. And so, if I graph this real quick, and this is where I'm going to have to do some cleanup tomorrow. What am I graphing? X to the 4th minus 7x squared plus 6x. Zoom 6 because I want my standard screen. Ooh, my standard screen now. Are you going to have to adjust a little bit?
Yeah.
Yeah. If I just change my y min, I'm guesstimating negative 20. I don't remember what it is. Okay, I didn't quite go low enough. Now I just went negative 30. Okay. Can I see my mins and maxes?
Yes.
Okay, this question is asking, decide if it has a, find the values, and state whether they're absolute or not. Okay, I'll show this, you can play on your own. Second calc, if I want to find a min, I have to pick number 3. If I want to find a max, I pick number 4. Minimum. So, notice the first question it asked me. Left bound. So here's a minimum, yes? I'm going to move to the left, and I'm going to hit enter. Sound familiar? Now it's asking me right bound, question mark. I'm going to move to the right and hit enter. Then it says yes, so now I'm going to move back to my minimum. And now it states minimum. You would do the same process with a maximum, yes? Okay, so I know the bell's getting ready to ring on me. Your homework is page 94. Actually, it's not 94, it's 93, isn't it? Sorry, some of my page numbers are off. 22 through 46 evens. The maxes and mins could be a little rough. But here's what I'm going to ask you to do. Try the calculator. Try them. See what you can do with them. And then you guys know I'll help you with questions tomorrow, right?
Yep.
Okay.
Wait,
And I am going to put the rest of this on the recording in case you want to look back at it. This guy would be an absolute minimum. This one is a local max. And this one is a local min. Find these. We used second and we use the min or max function.